Assalamu alaikum. Welcome to lecture 16 of data mining. So today we will continue and wrap up our discussion on classification. We had started talking about decision tree learning last time. So today we will discuss a few more ideas for decision tree learning. We will then talk about random forest. We will briefly also talk about boosting. And then if we have time, we will also introduce the k nearest neighbor classifier. So I think that's the agenda for today. And we do have a quiz at the end of session today at around 1:05. So I think from now onward, we will have quiz every week, and we have to take 4 more quizzes at least, so that we have at least 8 quizzes. So one quiz would be dropped before finalizing your grade. So, okay, any questions? All right. So any questions before I get started? So we were discussing decision tree learning, and so decision tree learning algorithms, there are 2 common algorithms that made decision tree popular. One is called ID3, which basically stands for iterative dichotomizer 3. And the other one is classification and regression trees. Both of them were proposed in the mid-1980s. And as I said earlier, decision tree made machine learning mainstream, made machine learning a popular application in many fields, from the sciences to the social sciences to the business community. And ID3 was proposed by Quinlan, and it basically proposes the use of entropy. And CART is both classification and regression. CART for classification uses the Gini index. So we had discussed both of these measures last time. So of course, the overall approach for decision tree learning is greedy, is divide and conquer. It's recursive. It splits the data using a splitting criterion, and the criterion, as I said, is based on entropy or Gini index for classification, and based on, let's say, sum of squared error or mean squared error for regression. So the tree, of course, is a data structure which has nodes and leaf nodes. The nodes, starting from the root, have decisions, or basically indicate decisions on attribute values. So depending on the outcome of those decisions, it will have a number of edges following that root or that node. And so let's say if you're talking about a particular attribute like gender, if gender is male, you will follow one path. If gender is female, you follow the other edge. So once you follow one edge, let's say gender is female, then you go to the next decision, which might be on another attribute, like let's say age. If age is low, then that's another decision. You follow the low path. And if you reach a decision, so decision node would have the label for that particular instance. And while training the data set, data would be filtered to each of those nodes based on the decisions that were made along the path. So, and of course, data will reach the leaf node as well. So how do you label the leaf node? So, of course, the ideal scenario would be that leaf node is homogeneous with respect to the class. So all examples that are filtered to a particular leaf node belong to one class. So in that case, of course, you will label it unambiguously with that class. But oftentimes, usually, the set that is filtered to a particular leaf node may not all belong to one class. So usually we'll then use the majority class to label the leaf. So let's say if you talk about a particular leaf node and we are talking about a two-class problem, so 25 example, let's say belong to the positive class, let's say, and let's say 45 belong to the negative class. So you label it as minus, which is a majority class. Of course, if you want to provide greater information, you might also give probabilities. So maybe you can say that plus with a probability or confidence of 25 divided by 45, 65, 70, and then plus uh, minus would be what? 45 divided by 70. So total number of data that arrives or is filtered to this node is 70, 45 plus 25. And among those 70 examples, 45 belong to the negative class. So negative confidence or probability is 45 over 70. And of course, the majority label would be negative. So this is how we actually label the leaf nodes. If it is regression, so this was classification. What about regression? For regression, so we typically label with the mean of values at a leaf node. So let's say at a leaf node, and let's say the outcome, let's say, is the price of a particular stock. Let's say at a particular leaf node, you have values of 25, 26, 28, and 30. So you label this node with the value which is the average of these, which would be, you have to calculate it, 25 plus 26 plus 28 plus 30 divided by 4. So 27.25. So you label this node with this particular value, which is the average or mean of all the values at that particular node. All right. So this is about labeling the leaf nodes. For classification, use the majority vote or majority class. And if you want to add confidence values, you can also add those. For regression, you can label it with the mean. And of course, if you want to have some confidence associated with the mean, you can also give a standard deviation for regression. All right. Okay, so now let's move on. So decision trees, as we mentioned last time, are a popular classification as well as regression technique. They are also easy to interpret because you can follow any path from the leaf node to the root node, and that would be like a rule. So for example, let's say gender is equal to male, and let's say we talked about age is equal to teen, and then maybe you reach the leaf node, and leaf node is, let's say, for example, buys a computer. So each path from the root node, from the leaf node to the root node is a rule. And the entire decision tree is a set of rules. So from the leaf node to the root node is one rule, and all such paths from the leaf node to the root node would be a set of rules. So in a way, a decision tree is also equivalent to the set of such rules. Okay, so what I wanted to mention now is that oftentimes decision tree would give you a tight fitting to the data. which is in the machine learning terminology called overfitting. So what does overfitting means? That you have learned the data exactly, but maybe there are noises and small errors and other deviations in the data. It will also learn that as well. But when you apply that model to other examples, it will perform poorly. So that in the machine learning community is called overfitting. Your model gives you low error on the training data, but higher error on the test set. Okay? So that is overfitting. And decision trees are prone to overfitting. One of the reasons is because it is a greedy approach. Okay? So now let's look at how to make and how to make decision trees more, you can say, improve the generalizability of the decision trees. So in general, overfitting is also related to the complexity of the model. If the model is complex, then it's likely to overfit, meaning that it's going to give low error on training data and high error on test data. So in the context of decision tree, complexity is directly related to the number of nodes or the size of the tree. And if you grow your tree to a great extent, you will get a complex tree, meaning that you have lots of nodes in it. So if your tree is simpler, it has fewer nodes, it's going to be less complex. And generally, less complex models would be less prone to overfitting. Okay? So, so after we have learned, so what are some of the techniques to ensure that we do not do overfitting? So there are two general categories of techniques. So one is called early, or what is known as pre-pruning. Pruning, of course, is reducing the complexity of the tree, and the other is post-pruning. And I'm going to discuss these two very briefly because this is maybe you will cover this in more detail in machine learning or some other course. But still it's important, so that's why I want to cover it. So pre-pruning essentially is of course, there are a couple of techniques here, but we are essentially going to discuss one, which is called early stopping. So meaning that when you are building the tree, you stop early. You instead of going deep, you stop at a certain point. And usually you can stop if your homogeneity at the leaf node is less than some threshold that you have specified. So for example, so whatever, let's say the entropy of the leaf node should be less than some epsilon. So instead of trying to ensure that or trying to force that leaf nodes are entirely pure, you stop at an early stage. So where the entropy is less than some value epsilon, which is close to zero, of course, but still not exactly zero. So early stopping is a common way of doing this. And of course, you can do it using a validation data set as well. So let me quickly show you that. So let's say if you plot, so this is your x-axis. X-axis is the number of nodes. Just give me a second. Okay, I want to hide this because there's a problem. All right. So let's say if you plot the error with the number of nodes. So if you increase the number of nodes, your training error is bound to decrease always on the training data set. But on the test data set, at some point it might start increasing. So that's the whole issue of overfitting. So as your model becomes more complex, which in this case is number of nodes, the test set error might increase after a certain point. So you will stop at the point where the test error starts to grow. So for this purpose, you will probably keep a separate test set during the training phase, which is often called the validation set. So this error, the first curve, the downward curve that I draw is on the training set, the upward curve is drawn on the validation set. And you will stop growing the tree when the validation error starts to increase again. So that is which says that the error on the test set, which is different from the training set, is high as compared to the training error. So this is early stopping. And of course, you can also do early stopping using the criteria that I mentioned before, E epsilon, the entropy is less than some epsilon. All right. So now what about post-pruning? In post-pruning, we have two approaches that are commonly used, which is one is called subtree pruning, and the other is called rule post-pruning. So again, here we have pruning. What is the effect of pruning? To reduce the size of the tree, to make it less complex, and as a consequence, give better performance on the test set. Okay. And one approach, one category was early stopping, which was while you're learning the model, you stop early, meaning that you stop before the model becomes complex or there becomes too many nodes. So in subtree pruning, essentially, I'm going to just describe it in a very abstract way. So essentially in subtree pruning, you basically start from the leaf node and take decision nodes and remove the entire node below that. So then you will compare the error after removal and before removal. If the error after removal on the test set has increased or has increased, then you will retain that removal. Otherwise, you will not remove it. So that's the basic idea. And you do it iteratively until you have reached a size of the tree that leads to the best performance on the test set. In the rule post pruning, you actually convert the tree into rules and then apply a similar process on the rules rather than on the tree. So similar process means that you delete entire rules or the conditions within a particular rule. So whenever you delete something, you check on the test set. If the performance has improved, then it means that that deletion is beneficial. All right, so let's move on. Any questions? So this was overfitting and the idea of pruning in decision trees and basically the way of handling overfitting in decision trees. So you have two categories, early pruning and then post-pruning, or sorry, pre-pruning and then post-pruning. Early pruning essentially is early stopping. Either you can have a condition like E epsilon is less than E is less than some epsilon, or you basically draw a curve on the validation set and check where the validation error starts to increase and stop there. And then the post pruning, there are two subcategories within that. One is subtree pruning, the other is rule pruning. So subtree pruning, we select subtrees that we would like to remove. So we will check if after removal, the performance has increased on the validation set, then that's a good pruning, and we do it iteratively. And similarly for rules. So now let's quickly move on to random forest. So even though decision trees are very popular, they're also quite accurate for many applications. They're and they're sometimes not as accurate as desired. So one way of improving the performance of decision trees uh, and one approach that has been proposed is called random forest. So these approaches are actually ensemble learning approaches. Ensemble learning means that instead of one model, you have multiple models and use the output of those multiple models to make a decision. So this is an example of ensemble learning. So previously we had built just one tree. Once that tree was learned or built, we used it for classification or regression. While in an ensemble learning, we will build multiple trees and use all of them collectively to make a decision. So specifically, it uses a number of ideas. So first of all, it's uses bootstrapping. So what is bootstrapping? Again, this is a general concept from statistics as well as machine learning. So bootstrapping basically creates multiple data sets with using random sampling with replacement. So let's say we have n training examples. Okay. So we will create, let's say, k or let's say s samples by simple random sampling with replacement of the n training examples. And this is simple random sampling, meaning that you sample uniformly. And what is the size of each sample? Is equal to n. So it means that each of the sample that you have created is also of the same size as the training data size. So what is random sampling with replacement? You generate a random number, you select one example. Let's say you generate a random number of the index to the example. Let's say you have 100 examples, 1 to 100 आपके पास index होगा. एक random number generate करें 1 to 100 के दरमियान, let's say 55 आया तो 55 का example select कर लिया. एक और generate किया 35 आया 36 select कर लिया. एक और किया 60 किया 60 select हो गया. Whenever you select an example, you assume that you have put that example back into the data set. Replacement के साथ है. So it means that maybe there is some chance that next time maybe 35 might be selected again. So that's fine. You select 35 again. Okay? So in general, but you will make up to n selections. So size आपका n ही रहेगा, 100 ही रहेगा, but there might be some repeated examples and maybe some examples from the training data set may not be present in the sample. So we will create, as I said, multiple samples and usually hundreds of samples because this is an easy process. So maybe S1, S2 to S, as I said, K, where K is maybe, I think, dozens, I would say even hundreds and hundreds. Okay? So that's one thing, bootstrapping. The second thing is you build a decision tree on each of those samples. So build just a second. Build decision tree on each sample. Okay. So you have k samples, each of the same size n. So you're building now k decision trees. So obviously, if you build a decision tree using any algorithm like the one that we studied earlier, on the same data set, you will get exactly the same tree. right? But now the data sets is slightly different, it's somewhat randomized. Not much different, but slightly different. So, so there is some chance that some of the models would be slightly different. So that's one randomization. The second randomization that we do is we restrict the choice of the features in each of those models. So instead of choosing from all M features or attributes, we choose from a randomly selected subset of these features in each of those models. So in general, we choose from a random subsample of the features each time. Okay? So this would also increase the randomness of the models. Okay? And help you overcome overfitting. Remember, overfitting occurs when your model tends to learn the noise and the nuances of the training data without focusing on uh, the data generating process. So these randomnesses would tend to avoid those issues. So usually the subset is oftentimes the square root of M. So let's say if you have 64 features, okay? So each time you will work with 8 randomly selected features only. Okay? And as a consequence also, when you work with only 8 features, your tree would also be smaller. Remember, the maximum size of your tree could be the maximum depth of your tree could be the maximum number of features in your data set. Okay? So if you are restricted it to 8, then of course your tree cannot grow beyond 8. So now what do we have? We have K decision trees. Each of those K tree has been trained on a sample of the original data set, and each of those is built using a subset of the original features. All right. So now we have an ensemble now, multiple classifiers, and each classifier is different from the other classifier, both in terms of the data set to some extent and the features. So now at prediction time, we will use all of those classifiers. So how? So let's say at prediction time, so, and if it is classification, so use the majority class from those K classes. So let's say K, let's say is 20, let's say, or binary classification problem hai. So 20K hai. So let me write it here. So let's say K is equal to 20. 10 give positive. 10 is not a good idea. Let's say 15 is positive, and let's say 5 is negative. So then best label is positive. Okay? So this is the random forest, meaning that first of all, it's an ensemble technique. It's a technique that is kind of avoids overfitting, and in general, it gives better performance than the standard single decision tree that we had talked about earlier. It uses 3 steps: bootstrapping, which is resampling with replacement. It then builds the classifiers on each of those samples by using a subset, again randomly selected, of the features. And then finally, it makes prediction by using all the classifiers by taking the majority output or label that is produced by all those classifiers. We are running out of time. Okay. Actually, हमारा time क्या था वैसे 1:35 था actually 1:01 नहीं था, so I'm mistaken, right? We still have time. ठीक है. All right. So this clear? All right. I can't see that. Okay. Okay. So this is random forest essentially. So very briefly, let me, by the way, bootstrapping followed by the majority vote approach, which is also sometimes called aggregation. So this is sometimes also called as bagging. So this approach of bootstrapping and then majority vote is called bagging. So in other words, random forest uses the ensemble approach of bagging. So there is another ensemble approach of called boosting. So boosting is another ensemble approach. And this one, I'm not going to go in detail, just give you an idea. Essentially, in boosting, we build multiple weak models. When I say weak model, you can say simple models. In the context of decision trees, these models would have few nodes. Sometimes they would maybe just have one node, which is sometimes called a decision stump. Just one node. ठीक है? Decision tree नहीं है, stump है सिर्फ. So one decision and then you have the class labels. But these weak models are built in a specific way. So essentially, so let's say if you build one simple model, you'll get some errors. Obviously, a simple model would not fit the data accurately, you will have errors. In boosting, you next time then work on just the errors and build another model. So once you have the second model, that would also have some error, then you work on that model and work on that set that is error and then build another model and so on. So that's the general idea of boosting. And then of course there are various techniques that can be done. So why I'm mentioning this is with respect to trees, we have the technique called the gradient boosted trees. So these trees use boosting, of course, and they use gradient boosting. Gradient basically is that you're optimizing the boosting process using a gradient descent approach. But essentially, they are an ensemble method based on boosting as opposed to random forest, which is an ensemble method based on bagging. And of course, again, you can use this to make predictions. Generally, gradient boosted trees are fairly accurate. They can compete with your best models, even with neural networks in many cases. Okay? So that would be essentially all that I want to cover regarding trees. So we started about simple decision trees, single decision trees. We looked at its algorithm, which is a greedy algorithm. Then we talked about the issue of overfitting in trees and how do we avoid or cater for that to that. So there are two categories. We have basically pre-pruning and post-pruning. And then we talked about some extensions to the basic decision tree algorithms. Both of these extensions are ensemble methods, meaning that they have multiple models. The first one was called random forest, which uses the idea of bagging. The second was based the gradient boosted trees, which uses the idea of boosting. And random forest and boosted trees are generally quite accurate in practice, and they are commonly used in practice. All right, so now let me quickly introduce another classifier, and that would be essentially all for classification. So the k nearest neighbor sometimes this is simply called a kNN classifier. Okay. So this is another simple classification technique. The roots of this technique are actually probabilistic, but you can understand it without looking at probability. And that's the approach that we are going to use here. So remember, we said that decision trees was information theoretic. So this is probabilistic. So that's one characteristic. The other characteristic is, of course, this is sometimes called a lazy model or a lazy learner. So we will see why this is called a lazy learner shortly. So this is another characteristic of this technique. So the idea is actually very simple. So let's say you have a training data set. Training data, of course, would consist of some features as a vector X and the class label C. Okay? Of course, you will have multiple examples, 1 to n. So the features X can typically be represented in some space, and depending on that representation, you can compute the similarity between two feature vectors. Okay? So let me maybe go to the slides. So let's say I'm drawing it in 2D. ठीक है? So 2D में मैं जब ड्रॉ करूंगा, लेट्स से मेरे पास दो क्लासेस हैं और क्लास को मैं रिप्रेजेंट कर रहा हूँ प्लस और माइनस से. सो प्लस के मेरे पास कुछ पॉइंट्स हैं 2D में मैं प्लॉट किए हुए हैं. these are प्लस के पॉइंट्स हैं और लेट्स से मेरे पास माइनस के कुछ पॉइंट्स हैं ट्रेनिंग के डेटा मेरे पास. ठीक है? सो ट्रेनिंग डेटा, सो लेट्स से मेरे पास ये ट्रेनिंग डेटा, मेरे पास कोई नया पॉइंट आता है, वो इधर है. अगेन पॉइंट्स में 2D में प्लॉट कर रहा हूँ, मीनिंग दैट आई कैन visualize or I can at least compute the similarity between points. So ये जो मैंने नया पॉइंट लगाया है, to which class is it closest? So it is closest to the positive class. Negative class तो बहुत दूर है इधर है. So it is more similar to the positive class as opposed to the negative class. So the best label for this would be positive. ठीक है? So this is the general idea. So we kind of make this more robust by saying that we compare the k nearest neighbors of this point that we want to classify. Nearest neighbor in the training data set. So I'm going to delete this and draw this again because I can't see the previous figure. So let's say मैं फिर बनाता हूँ यहाँ, ये मेरे पास प्लस हैं कुछ और यहाँ मेरे पास कुछ नेगेटिव्स हैं और मेरे पास कोई नया पॉइंट आता है इधर. अब let's say my k is, let's say 1, which is the most closest point to this. So most likely, I think it's the plus here. So if the closest point is plus, then this point would also be plus. So essentially, we label it based on the label of the closest point. So this would be 1 nearest neighbor. But usually 1 is not very robust. We will take usually k, which is larger. Usually k 3 to 7 use kiya jata hai in practice. So we will find the k nearest neighbors to this new point, and among those k neighbors in the training data set, I take the majority vote, meaning that maybe दो मेरे पास प्लस में से आ रहे हैं, let's say k let's say 5 है, दो प्लस में से आ रहे हैं और 3 नेगेटिव में से आ रहे हैं. So then this point would be labeled as negative. So this is basically the k nearest neighbor approach. So why is it called lazy classification? Because there isn't any, you can say, separate learning process in which you build a model. Like in a decision tree, you had the training data and then you built a model from the training data. Here, you don't have any model, you have just the data. And at prediction time, you simply take the new example and find which examples from the training data set are its closest, and based on their labels, you label this example. So it's a lazy model in the sense that it does not build a model a priori, it waits for prediction at prediction time. All right. So, of course, to make this algorithm work, we will need to have some measure of similarity between, let's say, 2 points x1 and x2. So we will have to quantify the similarity between two objects in our data set. So this algorithm, of course, would depend on such a similarity measure, and such a similarity measure is also essential for our next main task, which we are probably, maybe we can start today even because we still have time, 10 minutes, which is clustering. Okay? So you need to have a similarity function to be able to apply the k nearest neighbor, as well as for the clustering algorithms that we are going to study next. All right. So any questions? So any questions? All right. So if there are no questions, I think with that we will end classification in this course. So we will now move on to clustering or cluster analysis. So clustering is a key task in data mining, just like classification is a key task as well as association mining. Uh, so classification was primarily a predictive data mining, primarily predictive data mining. Clustering is primarily descriptive data mining. Uh, the outcome of clustering is in some way a descriptor or description of your data set, a summary or characterization of your data set. And that summary or characterization may not be readily be usable for prediction purposes. So that's why this is called descriptive modeling. On the other hand, if we talked about classification, the outcome was, for example, the tree, decision tree. So that model, that knowledge can be used for prediction readily. So that's why that was called predictive modeling or predictive data mining. So clustering is, as I said, descriptive data mining. The idea in clustering is to find groupings in data. Okay? So each group is a cluster. Okay? So each grouping is a cluster, and each grouping, of course, would contain some points in the data. But of course, this is not random grouping. It has to be based on some criteria, and in very simple sense, we want to obtain a grouping such that objects in one group are similar to each other, yet different from objects in other groups. So groups and clusters can be used interchangeably because, as I said, uh, a group essentially is a cluster which contains a number of points. So the grouping that we are desiring or the clustering that we are desiring is such that objects within a particular cluster are similar, but they are different from objects in other cluster. So this is very easy to understand in 2D. So in 2D, this is very easy to understand. So for example, let's say आपके पास कुछ points हैं. So let's say the so let's say you have some points in 2D, of course. So you can maybe form some groupings like this. So, and the two groups that are formed, the two clusters are formed within each group, the points are close together. So closeness in 2D space would be a notion of similarity. While if you talk about a point in cluster 1, that point is much far away from a point in cluster 2, but it's closer to a point within its own cluster. So we would like to find this grouping automatically. So originally we are just given bunch of data. So originally we are just given bunch of data. तो अब इस bunch of data में से we want automatically to be able to find groupings. So that would be the output of a clustering algorithm. So how many groupings that we want to find? So that's of course a parameter. And of course, for some algorithms, a parameter, for others, it can do it automatically. So we'll discuss that throughout this section. So the building block for clustering is, of course, the similarity measure of function. Sometimes you can also call this a dissimilarity. So similarity, dissimilarity, of course, are opposites. So you can maybe call it a dissimilarity function. Sometimes we also call it a proximity function. So you might also want to call it a relatedness, but that's less commonly used in the context of data mining and clustering. So we usually talk about these terms. So of course, dissimilarity is opposite of similarity. Proximity is more similar to similarity. So given two objects, x1 or xi and xj, we need to be able to quantify their similarity. So quantify the similarity or dissimilarity between xi and xj. Of course, xi, xj are representations of objects I and objects j. So as you can see, so we are talking about now again representations and objects for objects. So based on the representation, you may have different similarity or dissimilarity functions. So we will start with the simplest, and maybe I think that will bring us to the end of time today. So let's say if all attributes or features are numeric, which means that they are real valued, most likely ratio scaled, okay? And if all attributes are real valued, then of course you can compute the similarity, or in this case, dissimilarity between objects using what is known as the, actually the classes of function here. So in general, the Minkowski distance. So this is the general distance. Within that, of course, you are all familiar with the Euclidean and then we also have what is known as the Manhattan distance. And so on. So let's start with the Euclidean distance. So let's say you have 2 points, x1 and x2. Both of them are vectors, and they are represented by some number of features. So the Euclidean distance between them is simply the distance in Euclidean space between those 2 points. If you plot those points as points in Euclidean space, the distance between them would be simply the Euclidean distance. So in other words, the distance between x1 and x2 is simply the SQRT. So let's say x1 and x2 are vectors. Okay? So if they are vectors, then basically इसको फिर हमको लिखना पड़ेगा properly. So let's say x1 minus x2. These are vector subtraction. So vector generally would be a column, right? So I will transpose it to make it a row. And then this row vector would then multiply with the other column vector, which is also the same x1 minus x2. And of course, the whole thing is square root. So I think all of you know the Euclidean distance. You probably have studied this since O level, I would say. So if you are given 2 points in space, you can find the distance of the line connecting those 2 points as defined in this way. So if x1 and x2 are vectors, so difference of those vectors, take the transpose or take the inner product of the difference between the two vectors. By the way, the difference of the two vectors is the vector of the line connecting between those 2 points. And then, of course, then we have the length of that vector. So this is also sometimes called the L2 norm from functional analysis. So sometimes this is also called the L2 norm from functional analysis. So this distance is also called the L2 norm of the vector that connects those 2 points in space. Okay, so it's Occlusion distance. So the other distance is, of course, the Manhattan distance. So Manhattan distance is based on the absolute difference and doesn't have the square involved in it. So I think this would be better defined in terms of non-vectors. So let's say x1 or x2 हमने कहा था ना, let's say each of those has m features. So let's say j goes from 1 to m. So essentially then this would be, sorry, so we have the sum over j. Vertical bar is absolute. Okay, so x, so 1 j minus x 2j absolute, meaning that the difference between those two values, but we don't care about the sign. And then, of course, we sum it up. Okay. So this is the Manhattan distance. So this is in 2D space, it would be the block distance, meaning that either you, if you want to find the distance between these 2 points, so either you go this and then here, or you go here and you go there. While the Occlusion distance is a straight line distance. So Manhattan distance is the block distance, Occlusion distance is straight line distance. And of course, this distance is, if you compare it with the Occlusion distance, it doesn't have the square and the square root. Okay? It just, so that's why this is called L1 norm in functional analysis also. Okay? And in general, we have what is known as the Minkowski distance. So I think I'll stop after this. So Minkowski is basically, if I want to write it in terms of, again, elements, so we have, again, sum over j, okay? And then we have x1, sorry, x1j minus x2j raised to power of p, some p, and then, of course, the root to the pth root, 1 over p. Okay? So the special case of this is if you take p is equal to 1, you get Manhattan distance. If you take p is equal to 2, you get Occlusion distance. So we will discuss very briefly next time some properties of these measures and then move on to other measures. And then, of course, to clustering in general later on. So I think I will probably stop here. Any questions? So these measures can also be used in the k nearest neighbor classification problem. If your data set was described by numeric features, you could use these measures to quantify the similarity or dissimilarity between points and find out the k nearest neighbor for any given point from the training data set. Okay. Any questions? So start preparing for the quiz as well. So you have about 10 minutes. Quizzes, of course, are sequential in nature, and always try to keep a calculator handy with you while answering these quizzes.